All right, cool. We'll record. So, on to more derivative rules. All right, so we know how to do product rule and quotient rule and power rule, and we know how to take the derivative of trig functions. Today we're adding one final um, main rule to take in the derivatives. Okay, it's called chain rule. Um, it deals when we have function composition. So I'll get to that in a second. But for now, we got a warm up that says find the derivative of. I want you to change this actually to sine, if you wouldn't mind. Find the derivative of sine using the definition of a derivative. Um, and so we need to use the second definition of a derivative. So remember, we need to use this form right here. So that's going to be f of x plus h minus f of x over h. Now I'm going to let you try to do this. We'll go over this in class together, but usually I like to let you try to do warm-ups on your own. But your f of x in this case is sine of x. So think about how that's going to look, how you set that up. I will just go ahead and tell you off the bat, one formula or form you need to know is the sum and difference identity for sine and cosine. So if you have sine of a plus b, this is the same thing as sine of a sine of b plus cosine of a cosine of b. So you'll need that. And you'll also need the identities we talked about yesterday in our trig, the fact that the limit as x is approaching 0 of sine of x over x is 1, and the fact that the limit as x is approaching 0 of cosine of x minus 1 over x equals 0. So you need to know those two things. We talked about that yesterday. And let's see if you can reason through and try to set it up that way. It's a little bit difficult, and that's why we didn't learn it first. We looked mostly at the graph, but see if you can come up with it on your own. Okay. All right. Now on to what we're talking about with the chain rule. So product rule does the derivative when we're multiplying something, and quotient rule does the derivative um, when we're dividing something, right? Now what the chain rule does, what we're learning today, um, helps us take the derivative when we have function composition, so functions within functions, right? You've probably seen it in this form here, fog or fog or oh whenever we have three functions. But I guess another way you've seen it too is the way I prefer to write it is like f of g of x. That's the preferred way I like to write it. It's like whenever we have a function g of x within another function f. Okay. Or if you have three functions within each other, you would have like f of g of h of x. So it just means that you have one function within another within another. Okay. So in this particular example, number one here, it's kind of cut off. I just realized that there's supposed to be a 4 right here, raised to the fourth power. Okay. So we got to be good at being able to like identify what function is within what. Like we call it the inner function and the outer function. If you can identify that, chain rule becomes a little bit easier. Okay, so you've done this before. Like how about this? I'm going to say inner and outer. Okay. Like the inner function is what's like being inputted into a bigger outer function. So like what we're doing is we're inputting 2x plus x squared into x to the fourth. Do you see that? Like, do you see how this is nothing more than us taking this function and plugging it into x to the fourth? That's kind of the logic. That's kind of what we should be able to recognize. Like for instance, for this one right here, we'll start with the outer. I want you to be able to recognize that the outer function is kind of what this bigger part is, what we're doing to the inside. We're taking the cube root of x. And the inner function is what we're plugging into that. So that's x over 1 plus x. And this is a cool one right here. Number 3, this is like a function within a function within a function. Here's why. This is the same thing as, like, I'm going to rewrite this as secant to the 4th power. Like when you have secant 4th power of a quantity, that's the same thing as taking the secant of something raised to the 4th. That's the other way that we rewrite it. So what we do is we actually have a bunch of functions. Let's start with the outer. I think that'll be easier. The outer function, I think you can clearly see, is that we're doing some quantity raised to the 4th power. Okay, some quantity raised to the 4th power. Now, there's 2 inner functions here. So I'm going to write inner, I'm going to write inner again. The inner function is that we're doing the secant of something. The secant of some quantity x. Now, inside that, what we're doing is the square root of x. So what I want us to be able to recognize is that square root of x is being plugged into secant, and then all of that is being plugged into x to the 4th. So that's a function within a function. And we got to be good at recognizing that in order to do chain rule. Okay, we'll have plenty of practice with that. And here's just a chart that again, just kind of practices doing function composition. I mean, you can try this on your own if you want. I guess I'll do it, but it's nothing too crazy. You just always do the inner part first, right? So like g of 1 is 6, so that's like f of 6, which from the chart is 5. This is doing f of 1 first, so f of 1 is 3, and then g of 3 is 2. You can say f of 1 is 3, and then f of 3 is 4. G of 1 is 6, and G of 6 is 3. And I feel fairly confident in your ability to do this. G of f of 3, this is again saying, I always just put parentheses like that to specify that we're doing f of 3 first and then G of that. So f of 3 is 4, and G of 4 is 1. And lastly here, we're doing G of 6 first, which is 3. And f of 3 is 4. Okay, so this slide was all about just kind of refreshing ourselves on what function composition is. Okay, which happens, there's a lot of the functions we deal with. Okay, now chain rule can be stated one of two different ways. And honestly, guys, I write it just the first way. The second way looks a little confusing. I don't want you to worry about it. But again, just to specify, just to clarify, chain rule is used whenever we have function composition. Okay, function composition. Whenever we have an inner and an outer function. Okay. Now, the first way is the way we kind of wrote it in the last slide. Like if I'm taking the derivative, this is saying I'm taking the derivative of a function within a function. Okay. How you take the derivative is this formula right here. This is chain rule. Notice what we're doing. We're taking the derivative of the outer function while leaving the inside untouched. And then we're multiplying by the derivative of the inside. Okay. Now I'm not even going to bother going over how number 2 is read because it's saying the same thing but just using more calculus terms. But what it's saying is if I have g of x within f of x, the derivative of the function is the derivative. This is saying the derivative of the outside divided by times by the derivative of the inside. So it's just a fancy way of saying that. Now, what I circled up here, this is the derivative rule for function composition. This is chain rule. This is the way I prefer to write it. Let me explain, let me type out exactly what that's saying. All right, this is saying the derivative of the outer, okay, function with respect to the inner function which means the same thing as keep inner the same. Then multiply by the derivative of the inner function. Okay. Now, the reason it's called a chain rule is because we can have this happen more than once, especially if we have a function within a function. So something else to keep in mind that we're going to notice later is that the number of chains is equal to the number of inner functions. So what I have circled in red up here is pretty much stated right here in this sentence. It's the derivative of the outer function with respect to the inner function, which means to keep the inner the same within the quantity, and then multiply by the derivative of the inner function. So the number of chains is equal to the number of inner functions. So write that down, pause the video, do what you can, but that is essentially what we're doing. So like, I'll give you an example real quick before we move on. Let's say, it'll be a pretty straightforward one. How about y equals the square root of x squared plus 1? Okay. Now, what I want you to be able to recognize, and I'm not going to make you write this every single time, but I want you to recognize what your inner and your outer functions are. Like the outside function is you're taking the square root, which I'm going to say is like x to the 1/2 power, some quantity to the 1/2 power. And the inner function is everything that you plugged into that, which is x squared plus 1. And there is no function within that, so it's just one chain. So how this works, y prime is going to equal, and to help us see this, I'm going to write this as x squared plus 1 to the 1/2 power. Now, to take the derivative, we're going to take the derivative of the outside portion while leaving the inside untouched. So how would I take the derivative of like some quantity to the 1/2 power? Well, it's power rule. So I'm going to bring down the 1/2. I'm going to leave the inside untouched, and I subtract a power, so it goes to negative 1/2. So you see that we did the derivative of the outside part of it, x to the 1/2, while leaving the inside untouched. And then what we're supposed to do is multiply by the derivative of the inner function. So the derivative of the inner function, or the derivative of x squared plus 1, is just 2x. And that's my answer. Okay? I don't want you to overthink it. I don't want you to worry about it too much. It's not bad once you can identify the inner and outer functions easily. Okay? All right, let's keep going. So this is a pretty straightforward one. What's the inner? What's the outer? The outer function is just some quantity, and I won't write x so I won't confuse you, but some quantity to the 100th power. So that's the outer function. The inner function, what's being plugged inside of that, is x cubed minus 1. So how this derivative works is I'm going to take the derivative of the outside portion first while leaving the inside untouched. So that's going to be 100 times x cubed minus 1 to the 99th power. So I did power rule. I brought 100 down and subtracted by 1. And now I'm going to multiply by the derivative of the inside. The derivative of x cubed minus 1 is 3x squared. Okay. And I mean, again, I'm okay with you leaving it that way. You don't have to simplify it anymore. I guess if you really wanted to, you could combine 103x to 300x squared. I wouldn't suggest foiling to the 99th power, but again, I would just leave it this way. Okay. All right, what about the next one? We got cosine of x to the 4th power. So I'm not going to write it out again, but I think it's clear to see that the outer function is that we're raising to the 4th power, and the inner function is the cosine of x. So if I'm doing f prime of x, okay, I'm going to do the power rule first with the outside function. So that's going to be 4 cosine of x to the 3rd power. So that's doing the power rule. Bring down the 4 and subtract 1. And then multiply by the derivative of the inside. And the derivative of the inside is negative sine of x. Which, again, I'm cool with just leaving it that way. All right, that's the final answer. right, what about the next one? We got cosine of sine of x. So as you can see, the outside function is the cosine part. I'm taking the cosine of sine of x being the inside. So we're plugging sine into cosine. How is this going to look? Well, again, think about the rule. We're going to take the derivative of the outside while leaving the inside untouched. So the derivative of cosine is negative sine, and then we'll leave the quantity untouched inside. So we took the derivative of the outside as if there was nothing on the inside. And now we multiply by the derivative of the inside. The derivative of sine of x is cosine of x. So my final answer is negative sine of sine of x times cosine of x. And again, you can leave it that way. All right, what about the next one? Cube root of x to the fifth plus 7. So I think we can see that the outer function is the cube root part. So I'm going to write it so we can take the derivative pretty easy. Okay. So the derivative, doing the derivative of the outside part, the 1/3 is going to come down. I'm leaving the inside untouched. And I'm going to subtract a power, so that's negative 2/3. So I did the derivative of the outside, keep the inside the same. And we're going to multiply by the derivative of the inside, which is 5x to the fourth plus 0, which you didn't have to put that plus 0. All right. So not too terrible, I don't think. That's 17 minutes. I think I can keep going a little bit. All right. Debating whether I want to do. If I want to skip around, I'm trying to see if there's any problem that's better than the other to do. I want to leave some of these for class. I think we got a general idea of how chain rule works. Some of these are more fun than others. Yeah, I'll kind of keep going. I'll keep going because it's the next slide where I'm going to spend maybe a good discussion tomorrow. I want to leave something for tomorrow. Okay, so let's see. We got 1 over the square root of x squared plus 8. All right, let's first rewrite that. I think that's okay to see that this is the same thing as x squared plus 8 to the negative 1/2 powered. If you're given radicals, try to put it in a form where you can take the power rule. So this becomes like the last slide. I'm going to say the derivative, or we'll call it f prime of x, is equal to, I'm going to do the derivative of the outside part, which is just power rule. So I'm going to say negative 1/2 x squared plus 8, and the subtractive power will be negative 3/2 power. Okay. And then we're going to multiply by the derivative of the inside, which should just be 2x. And I'm okay with you leaving it that way. Don't worry about the negative power. You don't got to bring it down. You can just leave it that way. That's as much simplified as I really care. Okay. All right, what about sine of x squared? Now, if this was sine of just x, the derivative of sine is cosine, but we have an inner function now. We have x squared. So we're going to take the derivative of the outside part. Okay. The derivative of the outside part is just cosine, and we're going to leave the inside untouched. And we're going to multiply by the derivative of the inside, which is 2x. What about taking the derivative of sine squared? Now, you may not think that's chain rule, but it is, because remember, this can be rewritten as sine of x squared. Okay. And you can see that the outer function is something squared and the inner function is sine. So how we would approach this is power rule. So we're going to bring the power down. It's going to be 2 sine of x. And if we subtract the power, it's going to go to the power of 1. So you don't have to write power of 1. You can leave it that way. And then we multiply by the derivative of the inside. The derivative of sine is cosine. So sine squared's derivative is 2 sine of x cosine of x. All right, again, we got some funky mess going on inside of secant. So I'm going to take the derivative of the outside, leaving the inside untouched. The derivative of secant is secant tangent. So this is going to be secant, inside's untouched, tangent, inside's untouched. And now we're going to multiply by the derivative of the inside. The derivative of the inside is 2x plus 1. Again, leave it that way. Don't try to simplify it and mess up your answer. Okay? Okie doke. And then let's do these last two. Yeah. Okay, I definitely want to do number 6 because that's a good one too. So we'll do 5 and 6 and I'll call it. All right. The outside of this is that cubed. The inside is this mess right here. So what we're going to do, I'm going to do power rule. Power rule says to bring down the 3, leave the inside untouched. Don't take the derivative of that yet. So I did power rule first. And now we're going to multiply by the derivative of the inside. The derivative of the inside is quotient rule. So we got to do low d high, which is negative sign, low d high minus high, which is cosine of x, d low, which is 2x, all over low, or x squared plus 1 quantity squared. And that's it. Don't try to simplify that mess down, but notice what we did. We did the derivative of the outside, leave the inside untouched, times the derivative of the inside. Okay. Now I got one more for you before I end the video because I'm going to save this last slide for tomorrow. I recommend trying this on your own and trying any of these on your own, but we'll look at it. Okay. What's going on here is the outer function is x plus cosine x squared being raised to the 1/3 power. Now, let's try this out because I want you to notice that we have the inside function being x plus cosine of x squared, but what happens is we also have x squared as an inner function of cosine. So let's see how that derivative works. We're going to do the outside first, so we're going to do 1/3, leave the inside untouched, and subtracted power is going to be negative 2/3. And now we're going to multiply by the derivative of the inside. The derivative of the inside is 1 plus, what's the derivative of cosine of x squared? Well, it's going to be negative sine of x squared. But remember, we have another inner function. We got to multiply by the derivative of the inside there, which is 2x. Okay, so I had to do chain rule there twice. I took the derivative of the outside, left the inside untouched, and then when I took the derivative of the inside, I could do it with x, but when I took the derivative of cosine of x squared, that was another little chain rule within a chain rule. Okay, and we can discuss more examples of that tomorrow. So try to reason through that, see what you can do, and if you want, try this example on your own. Pausing the video at different times and just trying it. And then there's your homework, okay? It says 1 through 42. For goodness sakes, don't feel like you got to do all of those, okay? It's just practicing a bunch of different examples of chain rules and great problems, okay? So you can try those and we can go on from there. All right. Well, good job, guys. I am done for the video today. We will pick up tomorrow with it. And look at that, 24 minutes. Not bad. See y'all. Peace.